Ladies and gentlemen, up next, we have an innovation talk entitled AI for Space, presented by Dr. Steve Chien, co-head of the Artificial Intelligence Group of NASA's Jet Propulsion Laboratory at Caltech.
Okay, my first test is to find the clicker. Over here. Perfect. Oops. Okay, so it's my honor to be here to talk to you about some of the work that's been going on at NASA literally for decades. I'm going to start out by giving you a whirlwind tour of some of the main ways in which we've been using AI for decades, and then I'm going to finish up with what's my favorite topic, which is answering the question that should be in all of your minds, which is, are we alone in this universe in the hunt for life beyond Earth? So I'm going to use the meme, where we are and where we're going, where we've been, where we are, where we're going. So the first headline summary of where we are is AI is making a tremendous impact in space in many different ways. But the problem is, or the challenge is, it's a small proportion of its potential impact. I often get asked, what's my mission at JPL? My mission at JPL is to ensure that in the future, space missions have to explain why they're not using AI, rather than us having to endlessly explain why we should be using AI. And I already messed up my timing a little bit. I have to start this talk with a disclaimer that I'm here as a guest of SCSP. Anything I say here is my individual opinions and not the opinions of a sponsor or JPL or NASA. So anyway, moving right along here. So what are the two largest applications of AI at JPL? The first is machine learning for triage of large data streams. And we've heard a lot of this. How do you have your situational awareness in space? How do you have your overall situational awareness? And we have this in droves at NASA. So going all the way back to the 1990s, they were conducting a digital sky survey. It was called POS-2, which was at that time the largest catalog of all optical astronomy data that had ever been collected. That survey was actually classified using machine learning. Back at the time, there's a machine learning system called SkyCat for Sky Image Cataloging System, and that was using the precursor to what became random decision forests. Those of you who are into ML, you would know the history of RDFs, then SVMs, then more recently CNNs, and now all the transformer architectures. One of the big wins of this project in applying machine learning is that we did something called bootstrap learning. And this is work by Georgovsky at Caltech and Usama Fayyad, who was at JPL at the time. And so some of the data was captured at a higher resolution, digitized. Those are shown in the bottom frames. But most of the data was captured in the analog format, and you can see that at the top. And so we trained the machine learning on the lower resolution data, and the humans can only classify the higher resolution data. This actually enabled them to process several orders larger, more faint sky objects. And now it's quite routine that are what are called transient factories that are detecting all these anomalies in visible astronomical data, which might be things like supernovas and the like. These are all processed using machine learning pipelines, like the Zwicky transient factory. These science pipelines are actually relied on so much in the everyday operations of astronomy that the Zwicky transient facility data was actually used to confirm the LIGO Nobel Award-winning gravitational wave detection, because they have to rule out other possible explanations for the science phenomenon. We don't just do this with visible astronomy, we do this with radio astronomy, which generates even more data. This is actually an animation that shows what are called fast radio bursts. These are these unexplained transient RF data that come in and have to be correlated across multiple sites, all these terrestrial signals, and then they catalog them and try and understand where they're coming from. Some people will tell you that they're coming from alien civilizations. We can't rule that out, but am I going to say that that's the most likely explanation? I would refer to what Carl Sagan famously said, which is, extraordinary claims require extraordinary evidence. But where's the AI? Well, it turns out there's this great work by Kiri Wagstaff and David Thompson where they classify all of these events and correlate them across all the different sources. They did this in an effort called VFaster, which was detecting fast radio transit. That's the faster part of VFaster. And this work continues today in what's called the Square Kilometer Array, which is the largest sets of RF radio astronomy that are happening. So one of the challenges here is that for a lot of these data sets, you collect all this data and you actually have to immediately throw away the vast majority of it because the data set is just too huge. They have the same problem in high energy physics at CERN and these super collider events. They collect all this data from one of these events and they immediately have to figure out what's relevant and throw away the rest. Otherwise, they just don't have enough storage. So AI is very much being used. It's actually considered quite routine. There's actually programs and foundation models for earth science, for weather, for example, fire risk models are of great interest in the Western United States right now. Huge commercial impact. These are now considered routine applications of AI. So I would say they've succeeded in the sense that for them, people would ask, why aren't you using AI? Going beyond, there's even more use of AI in routine cases for semantic indexing of imagery. This is great work by Kiri Wagstaff where Mars Science Laboratory rover images are automatically classified so that the engineers can access them more easily. For scientists as well, this is Mars Reconnaissance Orbiter, high-rise imagery. These are all science phenomenon that people would be interested, so now they can submit queries, things like, show me all the Swiss cheese that happened in this geographical region of Mars in these seasons, and they can get immediately driven to that. There's even more work in indexing science articles where they process all of the science papers written about Mars, for example, from the LPSC, which is one of the major conferences, and now they can say, what other data sets should I be interested in given this is my paper, and it'll drive them to other data sets that people with common co-citations used in their papers, okay? And for me, one of the most exciting things going on here is we're driving acquisition of new data with these techniques. What do I mean? So on Mars, fresh impact craters are of great interest because when something hits, it exposes the underlying geology for just a little bit until there's a sandstorm or windstorm and it gets filled in. So this is work where Ingrid Daubar and Kiri Wagstaff automatically detect these fresh impact craters with low resolution imagery, and then they automatically bring in high resolution imagery, high resolution imaging assets to view this exposed substrate. So this is literally changing how we acquire the data. The second big application that you see is automated scheduling for operations of complex missions. So a lot of you are familiar with this image from the Hubble Space Telescope called the Pillars of Creation. What you might not know is that that image was acquired by the Hubble Space Telescope using a schedule that was scheduled by an AI system called Spike that was deployed in the early 1990s by our wonderful colleagues at Space Telescope Sciences Institute up the road. And this allows them to operate the very complex Hubble Space Telescope more efficiently. If we look to now, this is amazing imagery from the James Webb Space Telescope, which is a $10 billion one-of-a-kind asset. And this is a really unique instrument. It has this huge triangular thing, which is a sunshade that enables the spacecraft to take these unbelievable images of faraway objects, either galaxies or stars or things like that. And it's really challenging to schedule these observations. Long before it launched in 2008, they realized that one of the things limiting the lifetime is actually solar pressure on this huge sunshade. So if you take observations a certain way, literally the photons, the sunlight pressing on this huge sunshade will induce forces and torques on the spacecraft. And when these build up, you have to counteract them using your thrusters. That costs propellant, and that costs mission lifetime. So Mark Giuliano and Mark Johnston, two of the brilliant minds in AI scheduling for space, determined that they could develop this special set of strategies to minimize the momentum buildup and enable this $10 billion asset to have a longer mission. Even post-launch, they discovered that they were having a higher incidence of micrometeorite hits on the primary reflector, which is the mirror that enables all this amazing imaging. And we know where these micrometeorites hits come from. If you go out and if you're a space buff and you see the Leonid or Perseid meteor shower, it's the remnants of a comet, and then the Earth's orbit goes through it, and that's what we see. So they designed a special modification to the scheduling algorithm to minimize these micrometeorite impacts that enables them to last, for the mission to last longer. So AI is really making a difference here. JPL is very proud. They just launched what's called the NISAR mission. This is a joint mission with the Indian Space Agency. This is the world's most powerful and sophisticated sweep-SAR radar. It enables us to make these interferometric measurements of changes in the Earth's surface. What people might not know, this is one of the first light images of the coast of Maine, is that again, this mission is scheduled and the science plan is all developed in an AI planning and scheduling system called CLASP out of my lab. What about deploying AI on board spacecraft? This is now a dated video that shows the Earth observing one spacecraft. Literally in 2003, we uploaded our AI software to the spacecraft and operated it for over a dozen years. This spacecraft is the first spacecraft to fly machine learning operationally in 2004, support vector machine learning, and it enabled it to detect, understand what it was looking at in terms of the image cloudy, is the volcano erupting, is the ice freezing, and that enabled it to make decisions on what it would observe next. But what's better than one spacecraft using AI? Well, we actually linked together sets of spacecraft in a sensor web in order to enable one spacecraft to see something and request other assets with a complementary sensors like hyperspectral or thermal infrared or radar, and request that they observe the same targets that it just saw. So again, this is over 20 years ago we were doing this. But what's changed? What's changed now is now we have more advanced spacecraft. The access to space is cheaper. And this is a collaboration with Robotica and Open Cosmos. Something that we have flying on Cognizat 6 right now. We overfly a target, and we actually can look ahead and see where the clouds are and target around them. So we are taking the data, processing it through an AI pipeline on board a spacecraft, which was not designed for this kind of dynamic targeting strategy, in tens of seconds, and changing what we look at. And we're looking at custom designed spacecraft. We're going to drive this down to seconds. This has a lot of applications for the people in this room. Obviously, there's all kinds of interesting cross modalities like RF to Viz, RF to SAR, and things like that. We're also taking these technologies beyond Earth to Mars. We've had an autonomous targeting system on the MER rovers, the MSL rovers, and now the M2020 Perseverance rovers. So well over a decade, we've had this autonomous targeting system called Aegis. And for those of you who are Mars buffs, there's one common thing in all the images you see of Mars, and that all of Mars is covered with this rust-colored dust. Why is that? It's the iron oxide dust we see all over Mars. So they actually designed this LIBS spectrometer. It's a laser-induced breakdown spectrometer. We fire this pulsed laser, and that enables us to burn through that and actually then see what's underneath. And instead of manually targeting this, we have a system where the scientists can specify the kinds of rocks they're looking for, and the system, the onboard software, will hunt and find these targets autonomously and downlink that targeted data. And near and dear to my heart, because I spent 6 years of my life working on this, is the onboard planner on the Perseverance rover. The rover now has the ability to change the requested activities and execute them differently based on how the prior execution goes. If an activity fails, it knows to cancel the dependent activities. If it wakes up, it's colder than expected, it's going to take longer to preheat, it needs to adjust the plan. If it's warmer than expected, it can jam more into the plan. Also, just like your cell phone, we often realize that the battery is more or less charged than we thought, and we have to modify the plan. So this is exactly what we do. Proudly, there's not one but 4 AIs on the Perseverance rover. I already talked about the autonomous targeting. I talked about the onboard planner. There's another one called pixel adaptive sampling, where we hunt for specific astrobiology signatures and take more measurements of those. And then there's the autonomous driving. We are most proud of the fact that one of the most significant astrobiology discoveries ever accomplished by NASA for humankind, this recent discovery in this sample that was about a year ago, that's what's called Sapphire Canyon, is the sampling site. This is what's called an astrobiology signature level 1. In other words, we have no other explanation for this particular geological phenomenon other than ones that contain biological phenomenon, okay? Doesn't mean that it's the only explanation. It means we don't have another explanation right now. This sampling was all taken under the control of an AI system. Our onboard planner operated this 3-sol plan just as it has for the last 2 years. We've been operational since October of 2023, all done under an AI system control that replans on average 16 times per sol, or Martian day. So now I'm going to try and wrap up with where we're going. So first, we have this cadre mission to the moon, which is actually going to be 3 rovers plus a base station. And the team works together in order to accomplish tasks more quickly. So it can autonomously map by distributing out the areas that it needs to map and cover them more quickly using multiple rovers. And the rovers all coordinate so they don't cover the same areas. And the second thing it does is it does what are called joint measurements, which is using a ground penetrating radar. So here's showing you the divide and conquering to map more quickly. And then the next part is going to show the ground penetrating radar. And it's very hard for the rovers to coordinate because just like the Mars rovers, they're very power strapped. So most of the time they're asleep, even though this video doesn't show it. They can't stay awake for too long or they'll overheat or run out of energy, but they have to wake up. They have to schedule to wake up at the same times in order to coordinate. And then the second thing that I want to mention is we had the Ingenuity helicopter at Mars, which was a technology demonstration. The next generation Mars helicopter is a hexacopter called Science Chopper, and we want to take it to the largest canyon in the solar system, Valles Marineris. The reason why we want to go there is the same reason why all of us want to go to the Grand Canyon. If you look at it, you see the striations in the rocks, and the geologists call that stratigraphy. So vertical displacement means looking back in time at the evolution of the Mars geology. And so what we want to do is have the helicopter choose its own next targets. Choose its own next targets using artificial intelligence. And then going back to Earth, what's changing now? The changing thing now is we have proliferated LEO. So we have a demonstration called FAME where we're moving towards being on 8 spacecraft next spring, and eventually about a year and a half later to about 60 spacecraft, where it will be a multi-agent system. And the key thing here is these spacecraft are not designed to work together. It's what's called a federated system, where they actually are from different vendors, and these vendors are often in competition with each other. And we have a multi-agent system overlay where the scientists will specify workflows that will execute across these multiple vendors to accomplish their joint measurement goals. And so now, just with my little bit of time left, I'm going to talk about the thing that really keeps me at NASA, which is the hunt for life beyond Earth and how that requires AI. So I'm going to talk about 2 targets. One is Enceladus, which is one of the moons of Saturn. And we're obsessed with Enceladus because we know it has a liquid ocean, we know it has phosphates, and if you're really curious, those are the citations from Science and Nature. And so JPL has built this snake-like robot called EELS to go on a hunt for this life. And this is a really different kind of AI that this robot has to have. In the past, like on the Perseverance rover, the rover has to be able to make decisions to not break its own operations rules, but it's not really making science decisions on its own. In the future, these robots have to make their own science decisions. And what that means that when the rover is over here or the snake is over here, it knows it's far from any crevasse, it can move quickly. When it starts to get worried that it's near a crevasse, it has to pop its head up, which costs more time and energy to make sure it doesn't fall into a crevasse. This has special meaning to me because I'm an open water swimmer, and we do exactly the same thing when we're swimming in the ocean. When you sight to make sure you don't get off course, but you hate to do that because it costs you time and energy. And not only that, we want this EELS robot to understand, oh, that yellowish patch over there, that could be an astrobiology signature. Maybe it's worth risking going in between these two crevasses to go and see it, because after all, that's the purpose, that's why I'm here. Or maybe I should do that late in the mission. The other one that I'm going to talk about is Europa. Europa is one of the moons of Jupiter, and we built, again, this robot that would land there. And here's the problem. We land, we might survive 30 days, and we have to execute the policies that the scientists have made for us. And they're what we jokingly call astrobiology bingo. So you land there and you trench. Within a single trench, you can choose sampling sites. You have to decide what are the best sampling sites, both on engineering and science constraints. And then while you're trenching or while you're sampling, maybe it's going slower than you thought. So do you give up that trench and go to another trench? Do you give up that sampling site and go to another site? And then when you process the data, you may or may not find an astrobiology signature. If you find an astrobiology signature, the #1 priority is to confirm that. Nothing else matters. But by the way, you only have so much energy left, and you can't really measure how much energy you have left very effectively in your batteries. And you get 0 credit for finding life if you don't communicate it back to Earth. So these are the kinds of decision-theoretic judgment decisions that future AI has to make. And if that's not enough for you, one of the reasons why we're really excited about Europa is the scientists believe there's more water on Europa than on Earth. That's because the ocean is kilometers thick. But it's all below this icy shell, and they think that there are also hydrothermal vents at the bottom of this ocean. So one of the amazing things about science is it can be wrong and it can correct itself. So when I was a kid, first starting to study science in the 1970s, they thought life couldn't exist without sunlight, without photosynthesis. Then they discovered they were wrong. They discovered black and white smokers at the bottom of the ocean where an entire ecosystem exists without sunlight. So we want to go there and hunt for this life, but it's hard. So first we have to fly to Europa, then we have to land, just like the Europa lander, then we have to melt through this icy shell. And did I mention this icy shell could be kilometers thick and we don't even know exactly how thick it is? It could take over a year to melt through this. And we have to have a way of communicating back through this shell, so we need to have either repeaters or some kind of cabling. And then when we get there, we have an ocean submersible that has to travel thousands of kilometers, going out and hunting for this life and navigating back to a single beacon. And there are very sophisticated techniques to find your way back to a single beacon. They basically are synthetic motion-based trilateration. If you travel what you think is orthogonal to the location, then you effectively are setting up your own triangulation. And once your submersible is there, it has to go and hunt for life. If that sounds like science fiction, it is a little bit, but we're already practicing that. We've had not one, but 2 expeditions to the Gackle Ridge, which is the only known place on Earth where there are hydrothermal vents under ice. This is a collaboration led by Chris German and Mike Chikuba, who are the world-famous hydrothermal vent hunters from Woods Hole, and also with the Alfred Wegener Institute. But if that's not enough to get you depressed, excited, visionary, what's really hard? Going to another star. If you go to the nearest star, Proxima Centauri is about 4.5 light years away, but really what gets the astrobiologists excited is the TRAPPIST system, which is a little more than 10 light years away, because it has multiple Earth-like planets. Your cruise is going to be more than 100 years, and that space mission is completely on its own, because if you send it a direction, it's going to be 15 years before it gets it, and then when it sends data back, it's 15 years for you to receive it. That's the true challenge for AI in space. So with that, I'll lead you with JPL's mantra, which is dare mighty things. And I think I blew my time, so I don't know that there's time for questions, but I would encourage people to just catch me later on in the meeting. Thank you very much.